Hello and welcome to this tutorial. My name is Hervé Boeglen. I'm an associate professor at the University of Poitiers in France, and I'm going to talk to you about the mobile radio channel. Here's the outline of the tutorial. I'll first start with a little introduction, then we'll see the modeling of the mobile radio channel. And then we'll concentrate on simulation techniques using different software packages that are able to reproduce the main physical effects found on these channels. And then I'll finish with a conclusion. Here you see a classical digital communication system as defined by Shannon in his landmark paper in 1948, where an information source transmits digital data over a channel which adds errors to a destination. In fact, to avoid these errors, you need to use channel coding techniques, and these depends really on the physical channel behavior. So these channel coding techniques are not chosen at random or for the pleasure of the digital communication engineer, but because the channel imposes it. So in fact, as an example, if you've got a channel that's got frequency selectivity, you'll use a technique like OFDM. Now, if we look at the power variation we get at the receiving side of our communication system, we see that in fact these variations depend on a spatial or distance scale we use. There are three causes, and you observe them on three distances scales. So the first scale, the smallest one, when you've got movements around a few wavelengths, is called a small scale fading, and this small scale fading you see variation around a small scale average of about 10 to 40 wavelengths. The cause of that is the fact that you've got multiple paths which interfere with each other. Then what we can see is that the amplitude we see for this power variation follow a Rayleigh or Rice distribution. If you look at larger distances, let's say several hundreds of wavelengths, you get large scale fading. And large scale fading variation follow a log normal distribution and are mainly due to the shadowing effect of large objects which obstruct in fact the transmitting path. Again, it's average over several thousand wavelengths. Then the largest scale is simply the path loss, which represents the attenuation of the propagation wave with distance, and the attenuation is proportional to the squared of the distance between the transmitter and the receiver. In what follows, we are going to be interested really in the small scale behavior of the channel, because this is an effect that you cannot easily compensate for with the electronics of your receiver, and you will find these effects on the baseband digital signal that you're going to use. When you look at the main physical effects on the mobile fading channel, the first one is the multipath propagation. When the transmitter transmits the digital signal to the receiver, the electromagnetic wave interacts with different objects that you find in the environment, and with phenomena like diffraction, scattering, and reflection, you've got the creation of several copies of this transmitted wave. You can also have a direct path, which is called the line of sight or loss path, as you can see on this figure. So if you look what happens at the receiver, I have just to remind you that it's a digital receiver, so you find in fact a sum of impulses, direct delta functions, representing the different paths that come from the environment. They are separated by different values of tau, tau being the delay representing, in fact, the length of the path that the path travels. So this is typically what we call a channel impulse response, and it depends on the variable tau. If you take the Fourier transform and you look what happens in the frequency domain, you see that you get the figure of you've got on the right, and you see that it's not flat. In fact, if you transmit something over this channel, you will see that the different frequency of your spectrum are going to be distorted differently. So what we can see here is a spectrum distortion of the transmitted signal. The second effect is when the transmitter or the receiver are moving. So here you can see a car and which is moving from the left to the right with a speed v. So what happens is simply that the transmitted signal spectrum undergoes a frequency expansion. So this frequency expansion is in fact gives you the max Doppler frequency represented by this equation. So it's simply the speed of your mobile divided by the speed of light and multiplied by the carrier frequency. Depending on the path, you can have different f max, because it depends also on the cosine of the angle of the incident wave. So the consequence on the channel impulse response is that it becomes time dependent, and you can see this with this little animation. You see that the amplitude and also the phase that is not represented here, they change over time. So the consequence is that on the spectrum you're gonna have also changes, and you see here the effect of what is called frequency selectivity. So when we want to model this mobile radio channel, we can say that it's a linear system having an impulse response, and this channel is a bit special in the fact that you've got two variables, namely t and tau, and this channel impulse response is represented simply by the equation here, where you see a direct delta impulses comb. The different delta are delayed by tau of n of t, and they are also multiplied by a complex number with an amplitude alpha of n of t and a phase phi of n of t. The representation, you've got an example of representation on the right. So it's a two variable system. So when we study the behavior of such functions, we look for a variable than the other. So what we start now with is to say that our channel impulse response doesn't depend on t, and we look what happens when we've got two or more propagation paths. Example 1 to example 3 on the figure. You see that if you look at the channel transfer function, the module, you see that some frequencies are attenuated, and this can be quite severe, under minus 30 dB. The more propagation path you get, and the more fluctuation you've got. So the worst being, as you can see, example 3. This just represents the physical effect of the interfering between the different paths, either constructively or destructively, because it's a complex number. You have to remember that. So that's really the frequency selectivity. So what happens with the delay duration, and we are going here to consider the tau max, that is the maximum delay we find on a channel impulse response. Two examples here, 1 microsecond, 5 microseconds. If you take the inverse of these values, you find 1 megahertz and 200 kilohertz. And this simply represents, if you look at the signal on the transfer function, a kind of stability region. So it's the width of the stability region you are able to find for these channels. So what you can see here is the larger the tau max, the more selective the channel. Another consequence of frequency selectivity is inter-symbol interference, because we transmit digital data on this channel. So digital data the different symbols are going to interfere, and then the bit error rate is going to be higher and is going to degrade. So the more frequency selectivity, the more ISI as well. So at this point, we can distinguish between two types of channels. So the first one is the narrowband channel. We suppose that we transmit digital data with a symbol duration of TS, and in this case TS is much larger than tau max. So the bandwidth of the transmitted signal is represented by B, is 1 over TS, and as you can see, the bandwidth is not really influenced by the channel. It's quite constant, because it's small considered to, if you compare to the frequency stability region of the channel. So low frequency selectivity, and therefore you won't have much ISI. Now if you consider the opposite, which is the broadband channel, in this case you've got TS that is much smaller than the maximum channel tap delay. So the bandwidth of your transmitted signal is quite large, and of course it's much larger than the stability region of the channel. So you've got really frequency selectivity, as can be seen on the figure, and also high ISI. So now let's consider the time. So we take into account the two variables, and this time we look at the transfer function over time, with two propagation paths up to many propagation paths. And as you can see, they've got different Doppler frequency. This is simply because the incident angle of the different paths are different, so different Doppler frequencies. Same behavior as before. Over time, you've got fading regions, in fact, at different times, and the more propagation path, the more variation over time you're going to have. So again, if we take two different values of the Doppler frequency, so different value of speed of your mobile, you see 100 Hz and 500 Hz, for example, too. It leads to the time stability region that you can observe on your transfer function, in fact. So time variance increases with higher Doppler frequency, so with higher mobility. So now, as a summary, we can have four types of channel. They are either narrowband or broadband, or time variant or time invariant. So the worst one is the time variant broadband channel. It's the one that is on the bottom right. Frequency selectivity and a lot of inter-symbol interference. After having seen the main physical phenomenon on these mobile fading channels, let's introduce two models that are very much used in practice, and these are the relay and rise channel. So the relay channel is a channel with only one path, so it's a narrowband channel, and the received signal is a superposition of a large number of subpaths, and it's important to notice that it's without a line of sight path. So the I and Q receive components follow a Gaussian distribution, and if we take the module of these two components, we see that it follows a Rayleigh distribution, which is represented here on this slide on the left, and considering the phase, we see that it follows a uniform distribution between -pi and +pi. If you take into account now a line of sight path, it becomes a rise channel. So this line of sight path can have different power values, and in fact to define that we use the rise K or C factor, which is simply the power of the loss path, which is S squared over the power of the n loss path. You've got a special case for K equal to 0. It becomes a Rayleigh channel again. If C or K is larger than 0, you see that the amplitude samples follow they tend to a Gaussian distribution. If we compare the transfer function of a Rayleigh channel and a rise channel for here a Doppler frequency of 200 Hz, you see that the power fluctuation of a Rayleigh channel are considerably bigger than on a rise channel. So that's important to notice. The worst case is really the Rayleigh channel. So up to now, we've considered that the mobile fading channel could be modeled as a deterministic process, but it's easy to imagine that it's not possible, since it would mean that to modelize this channel, you would be able to modelize all the elements in an environment with the material properties and of all the elements, for example trees and building and everything. It's just not possible. So what is done in practice is to consider that it's a stochastic process, and that the channel response, impulse response, can be characterized by an autocorrelation function, which is represented by the first equation on this slide. And the second element for the approximation is also to suppose that the stochastic process is going to be WSSUS, meaning that it's White-Sand stationary, meaning that the autocorrelation function does not depend on t. And second thing, the different paths are not correlated, meaning that they've got a different physical origin. That's really important, and this approximation is the most well known and well used in practice. Starting with this autocorrelation function, which now is no longer called a channel impulse response, but a channel intensity profile, you can, with the two variables again, tau and t, if you take a Fourier transform, you can obtain different functions which will give you different views of what's happening on the channel, and also it will allow you to get interesting parameters that we use to design digital communication systems. For example, starting with the frequency time correlation function, you can have the coherence time TC and also the coherence bandwidth. With the channel intensity profile, you can get the mean delay spread and the RMS delay spread, which are really used quite a lot in practice. So if we consider now the power delay profile, setting the T to 0, this represents simply the mean power that is associated to a path with a given multipath delay. It can easily be measured empirically, and this allows us also to calculate two parameters that are really interesting for digital communication system design, which are the mean delay spread and especially the RMS delay spread. It's a way of qualifying the frequency selectivity of the channel. Another important characteristic is the coherence bandwidth. You can look at this coherence bandwidth as the frequency stability region we were talking at the beginning of this presentation. In fact, when you take the Fourier transform of the channel response on this function, depending on the frequency, you can see the coherence bandwidth. And in fact, a commonly used approximation is given by this equation, is simply 1 over the RMS delay spread we just seen before. Concerning the Doppler spectrum and the coherence time, again, if you look at the different functions we had before on slide 22, if you take the Fourier transform of the frequency time correlation function relative to t, and you want to characterize the Doppler frequency at a single frequency, you just set delta f to 0, you can get the power Doppler spectrum, which is simply a Fourier transform of an autocorrelation function. It's given by this equation, and the maximum value nu for which this function s of h of nu is non-zero is called the Doppler spread, and is denoted BD. BD is the Doppler spread. It's a Doppler frequency, in fact. So the time during which the function phi h of delta t is non-zero is called the channel coherence time. In fact, it's also a notion, an aspect we've seen before, is the time stability region on your frequency, on your transfer frequency function. So a commonly used approximation for that is that the coherence time is related to the coherence bandwidth by 1 over TC. So BD is 1 over TC. If you look at the Doppler spectrum and the shape of the Doppler spectrum, one very well used in practice is the Jake spectrum, this bath tube shape. It's quite common, commonly used in practice, and we will reproduce it in the simulation part that we will see afterwards. So in summary, for the mobile radio channel, we can say we have to recall that it's a stochastic process, that it can be analyzed and modeled using statistical tools, and it has also to be analyzed in the time and frequency domain. That's really, really important, as this figure shows it here. If I take a slice in frequency, I can get information about the Doppler shift, and if I take a Fourier transform on this Doppler shift, depending on time, I get the Doppler spectrum as we've just seen before. And if I take a slice in the time domain, I get the delay spread, which allows, thanks to a Fourier transform, to see the channel transfer function in the frequency domain. So now let's have a look on the techniques to simulate this mobile radio channel. So we want to be able to simulate because the measurement system that would be needed to qualify a channel, to have all the physical effect of a channel, it would take a lot of time because you need a lot of data, and moreover it would need a specific tool called a channel sounder, which costs an awful lot of money. So if we've got tools that can simulate quite precisely communication channel, that's really good. So the two main techniques, simple techniques we use, is the first one is the filter method, where you generate a unit variance Gaussian process, which is a complex process, and the real and imaginary part, you just pass these values into a filter and you just sum it, and this is going to give you for example the Rayleigh channel, and this is what we're going to simulate in the last part of this tutorial. Another possibility to generate the same type of coefficients, again complex coefficient for a Rayleigh or a Rice channel model, is to use the sum of sign method, where you see that you've got a sum of different cosine with different frequency and phase angles and coefficient that you sum, and this method is quite efficient in terms of processing power, and it's due to Rice. When you've got more than one path in your channel model, it means that you have to use either the SOS method or the filter method several times. If you have got 6 times, you got to use 6 generators, and these generators are added after different delays, the delays of the physical channel response, and it leads to a structure called the ATAP delay line, as you can see here on the slide. So now let's talk a little bit about normalized mobile radio channels. In fact, these models are quite well known and used in practice, but they depend on the digital system you want to simulate, and also the amount of bandwidth you use in your system. For example, here the COST 207 is a set of channel models that have been designed for the deployment of the second generation mobile telephony, GSM. So you are not supposed to use them for signals that are not GSM or with a bandwidth that is much bigger than the bandwidth you find on GSM. But a lot of people tend to use them for much higher sampling frequencies. But anyway, you've got specific models for 3G telephony, 4G, also for example, digital audio broadcasting. So be careful when you use this model to look at what they were supposed to be used for. So, for example, here I've got a model that is called the typical urban. So it means that what the people who have created this model have done, they've simply done intense measurement campaigns on different cities in Europe, and they've extracted the main statistical characteristic of this model, and it has become this model. So 6 paths with the delays represented here, the propagation delay, and then the relative path power in linear or in dB, and also the shape of the Doppler frequency. So the JX is the one, the bath tube we've already seen, but we see here that for path 3, 4 and 5 we've got different shapes. So you have to, if you want to reproduce precisely this model, you have to be careful about the filter you use to filter your samples. So you have to know also that these models are integrated in modern signal generators, which are used by digital communication engineers. So it's really they are very much used in practice, and it's they are precise enough to validate a digital communication algorithm. So now what's interesting to look at also, we'll come back to that with the simulation, but is to notice that the beta error rate on a Rayleigh channel is going to be much worse than the one you will find on an EUGRD channel, as you can see. So these bit error rate values are not compatible with transmission of, for example, images or things like that, because you need much lower bit error rates. So that's going to be a challenge with digital communication techniques to reduce this bit error rate values. And if we look now at a transmission, 16 QAM transmission using lab equipment, on the left you've got the EUGRD channel, which is quite easy to recover the data because in fact all the different points are really at the not far from the theoretical decision region, whereas on the right you've got the same transmission on a Rayleigh channel. As you can see, the constellation is dancing. You see the phase rotation induced by the channel, and also the variation in the amplitude. So that's going to be really tricky to decode. So let us now start with the demonstration part of this tutorial. Firstly, I propose to generate some Rayleigh channel samples using the filter method we've just seen in the previous slides, and also to trace our BR curve for this channel using the Octave software package. Then I switch to MATLAB and the communication toolbox to show you the concept of resolvable paths for a frequency selective normalized channel model. And then I'll switch to GNU Radio with our QPSK digital communication system built around a Rayleigh channel, which is not frequency selective. And then I'll show you how to configure a frequency selective COST 207 typical urban frequency selective channel using the GNU Radio blocks. Don't forget that the files I'm going to use for this demonstration are available on my GitHub, so don't hesitate to get them and work with them at your own pace. So now let's start with Octave. And with Octave, the first thing we are going to do is to simulate a Rayleigh channel. So we are going to generate Rayleigh coefficients. So the first thing we start to do with this script is to generate a unit variance wide Gaussian complex process. So it's quite easy to do, in fact, with the rand_n function. Then we define a Doppler spectrum filter, which is a Jakes filter we've seen before, and this is defined in the frequency domain. So we come back to the time domain in order to perform a convolution using an IFFT. Then we resample to our system sampling frequency. So let's execute the script and see what happens. So on the left you've got the amplitude, which is scaled in dB volts, and as you can see, and as expected, you've got variations that can be quite important, going down to minus 40 dB from the average. But we also have the phase rotation for all the samples. Don't forget that you generate a complex process, so you've got the real and the imaginary part, the phase shift as well. On the right, on figure 2, you have got the shape of the Jakes filter we've just generated for a Doppler spread of about 100 Hz. So as you can see, it's quite easy to get these samples. Now, if we want to look at how to obtain a beta rate curve for this channel, if you don't take into account something quite important, you won't get exactly the curve that is expected, the one you find in specialized books. So for example, if I don't take this parameter into account, I'm going to have a Rayleigh curve that's an horizontal curve simply. So it means that the BER is maximum, so there's something wrong with it. And in fact, what they suppose in the books when they trace this BER curve for the Rayleigh channel is that you've got a mean to estimate and compensate for the phase shift induced by the channel. So how do we do that in simulation? But quite simply by taking the output of the channel and multiplying by the complex conjugate of the Rayleigh process we've just generated. Okay, so let's see now if this works. Yeah, okay, this time it's okay, as you can see. So another thing to notice is that the BER curve is much worse for the Rayleigh channel than for the EUGRD channel, so you have to take care about that using communication techniques that's going to improve this BER. Otherwise, it's going to be difficult to transmit digital data, like for example digital images. So now let's have a look on what's happening with MATLAB. So I'm going to use here MATLAB and the communication toolbox. So I want to show you the concept of resolvable path. So I generate here two channel samples for a Rayleigh channel, which is frequency selective because I've got 6 paths. And you see the two channels, the only difference is the sample rate. So in the first case, I'm going to use 20 kHz as a sample rate. In the second one, it's going to be 2 MHz. I'm going to look what is going to be the consequence. So if I start the simulation for the first case, I see that all the 6 paths come at the same delay almost, and that the frequency response is flat. So it's a frequency non-selective channel, although I've got 6 paths. Now the sampling time is 2 MHz. I can distinguish the 6 paths, and as I can see, the frequency response becomes selective. Okay, so that's the notion, the concept of resolvable path. So the channel is always the same. It depends at what speed you sample it. Okay, so at a low sample rate it can be non-frequency selective. This was the first case, or it can be highly frequency selective when your sampling rate is higher. Finally, the last two figures show simply the 6-path generated coefficients in amplitude on the left and the phase trajectory on the right. Okay. So now let's switch to GNU Radio, and in GNU Radio I've just designed a communication system using QPSK. My sample rate is 4 megahertz, okay, and I use a fading model block that's available in the library, and also a channel model block, which is here to model the EUGRD contribution. Okay, so for this case I use a non-frequency selective channel. It's simply a relay channel here. As you can see, the generation method uses the SOS, the sum of sign model we've just seen previously in the slides, and it uses the normalized max Doppler frequency, which is simply a way to normalize that you will find in a lot of simulation systems. It's just the product of your max Doppler frequency multiplied by the sample time of your system. Okay. So now if I launch the simulation, what I'm going to observe is the dancing constellation if I don't do anything to estimate and to correct this phase rotation. As you can see, the spectrum of the QPSK modulation is quite clean. You see that all the frequencies fade at the same time. There's no frequency selectivity in this spectrum. And if you look at the last constellation, I've just implemented a small equalizer that estimates the phase rotation so that I can recover correctly my data. So that's a relay channel without frequency selectivity. Now I've got the same channel model we've already seen a few times, several times now. Is the COS 207 typical urban channel. It's possible to simulate it with a frequency selective fading model block that you find in the library. You just have to take into account two elements. The first is the power delay profile we've already seen. It's not you don't enter the delays in tau values. You have to enter these elements in samples. For example, if I take the last path, the 6th path in the table you get for this model, it says that it's got a delay of 5 microseconds. So 5 microseconds with my 4 megahertz sample rate transforms in 20. So I've got 20 samples. Okay, I have to input it like that. So 20 samples for the last path. And for the PDP magnitude, it's not in dB, it's in linear. So you have to be careful also about that. Same model to generate the coefficients. It's the SOS model. Okay. So now we are going to look at what's happening, and that's typical of a frequency selective channel, because you've got several points on the constellation, and if you look carefully at the spectrum, you'll see that some frequency fades differently from others, so showing that we are with a frequency selective channel. That's the worst case. So again, I have designed an equalizer to counteract the effect of this frequency selectivity, which works, as you can see, quite well. So that's a frequency selective channel. Okay, let's go back to our presentation, and we go for the conclusion. So the mobile fading channel is really the real world. Yes, in fact, your mobile phone, Wi-Fi, digital audio broadcasting, digital video broadcasting, all these digital communication systems use mobile fading channels. So it's something that is the reality. The worst case for this channel is the time and frequency selective one. So when you've got time and frequency selectivity, you can expect a very high BER value. So there's a need clearly for sophisticated digital communication techniques. For example, OFDM. It's a technique that my colleague is going to talk to you about after this tutorial. Also interleaving in the time and frequency domain, spread spectrum, etc. Okay, we come to the end of this tutorial. I thank you for your attention, and I will simply hand the floor to my colleague for the next tutorial. Goodbye.